Hello everyone. So here we are going to start chapter 5 part 3 recording. So in this recording we will see that how we solve a piping network using Hardy-Cross method. So when we have a when we have a piping network, so this is one of the example of the network having two loops here. So there is some given information and some information we need to find out. So the flow rate going into the network is given here, and the flow rate that is going out of the network is given here, this value and this value and this value. So our objective is to find out certain things, for example, that determine the flow rate in each line. So by just knowing the flow at the exit, we cannot determine, or we cannot directly determine basically what's the flow rate here. Let's say this flow rate here Q1 and the flow rate here is Q5. So we don't know how much is Q1 and how much is Q2, and here is how much is Q4 and how much is here Q2 and how much is here Q3 and how much is here Q6 and Q7. So by analyzing this network and solving the problem, then we will be knowing that how much is the flow rate in each line and what is the correct flow direction. So for example, like the fluid is coming from here and then it is traveling into the network, so the direction of this is obvious, that the fluid is going in this direction, and from here and here. So there are two possibilities, that fluid is going here, so it may come down, this is one possibility, and when it is coming down and coming down from here also, so in this we don't know where the fluid is moving, whether fluid is moving in this direction or moving in this direction. So basically the objective to solve the problem is that we basically want what is the correct direction of the flow. Determine the head loss in the element. So we need to find the head loss in each element. Let's say this is element AB, and then from B to E, and then from E to D, or D to E, whatever is the flow direction, and then from A to D. And similarly for this loop. So we need to find the pressure drop in each element. And then finally we need to find, like, if this is connected with the pump as we discussed before, then what is the net head from point of inlet to the exit point, from this to this exit point and to this exit point and to this exit point. So these are the questions that we will answer when we solve this network. So the given information is the flow rate at the inlet and exit points, and the length of the each element and the diameter of each element. So how do we do this then? These are the steps that we need to follow. So the step number one is that first of all we need to assume the direction of the flow in each element. So this will be our assumption. Check the continuity for the entire network, that is how much is the flow in and how much is the net flow out. So like the flow in, and that should be equal to the flow out. Check the continuity for the entire network and write the continuity at each nodal point. So continuity at each nodal point, like this is a nodal point A. So for A, if we are going to write the continuity at each nodal point, then the fluid is moving in this direction and in this direction, then at the 0.125, this should be equal to Q1 plus Q4. So this is the meaning of the continuity equation at each nodal point. And then simplify the equations, identify each loop. So these are the steps, and then we will do it, then we will understand more about these steps. So let's do the first step, that checking the giving the direction to the network. So here it is that we have given the direction, that the line A, the fluid is moving in this direction, and the line 4, the fluid is moving in this direction, and the line 2, the fluid is moving in this direction, and the line 3, the fluid is moving in this direction. Similarly, in line 5, the fluid is moving in this direction. So these are our assumed directions. The step 2 is to satisfy the continuity for the entire network. For the entire network, the continuity is that the summation of the Q in is equals to the summation of Q out, whatever is the flow. So the Q in, the number of inlets are 1 in this case, so which is 0.125, and that should be equal to the exit flow rate, which are 4. So this is the Q in and this is Q out, so this should be equal. So we need to make sure that the continuity is satisfied here. Then the third step is to set up the continuity at each node. So this is the network node A, B, C, D, E, and F. So these are the six nodes. This is A, this is B, this is C, and then D, E, F. So here, as per the given direction, because the direction of the flow we have already assigned, so here for this node, for node point A, we can write the continuity equation that 0.125 is equals to Q1 plus Q4. So this is for nodal point A. Similarly, for nodal point B, we can write that the Q1 equals to Q2 plus Q5. And for nodal point 3, we can write, similarly we can write for nodal C we can write, and then for nodal D also we can write here, and for nodal E we can write, and then we can write the nodal F, which is here. So we can write the continuity at each nodal point. Now see how many are these equations? 1, 2, 3, 4, 5, 6. Now we need to simplify these equations because we want to solve them. So if you write the simplification, then write that these equations in this form, that here the Q1, 2, 3, 4, 5, 6, 7, it is up to 7, so we can write the later one in terms of the previous one. So the Q4 in terms of whatever is in the equation, the Q1 is in the equation, so in terms of Q1. Similarly, from this equation, the Q5 in terms of Q1 and Q2. So the Q5 in terms of Q1 and Q2. And from this equation, the Q6 in terms of Q5. But the Q5 we already have here, so you substituted here in this equation this value. So you substitute the Q5 this value, and then write that the Q6 is equals to this thing. Similarly, this is in terms of Q4 and Q3. So we have already found the Q4. So when you substitute the Q4 here, so you can write this, that the Q3 equals to in terms of Q1. From this equation, we know that how much is the Q3. The Q3 we already have, so you substitute the Q3 here, and then you write here that what is your Q7. So this way, we can write this equation, these equations, like the one for Q4, one for Q5, one for Q6, and then Q3, and then Q7. So from this equation, either you can write in terms of 6 or 7, right? But both of them we have already, Q1, Q7, and Q6. So this equation will not help us. So this equation we can leave, and here these are our consistent equation. So 1, 2, 3, 4, and 5. So we have 5 equations which are consistent in this system. So there are 5 independent equations and there are 7 unknowns. So we cannot solve this system, so unless we do some simplifications. So one of the simplification is that you can use some reasonable value for Q1 and Q2, and then basically you can substitute this Q1 and Q2 in these equations to find all, like Q3. So the Q1 and Q2, these are the two that you assumed, and then substituting back into this set of systems of equations, then you can find what is your Q3, Q4, Q5, Q6, and Q7. So this way you know all of the values of Q. And remember that here all the Q's are coming out to be in positive. So initially when we assume the direction and the value at the end is coming out to be positive, that means your assumed direction is correct, because all the values are positive. If negative, then you make it positive and change the direction here if any value comes out to be negative. So now we are here that we know all the flow rates. So this was our step number 4. Now moving to step number 5. Identify the loops and assign the positive direction. So identify the loop in your system. So we have two loops. This is one loop and this is loop 2. So we identified that there are two loops in this system and we given the direction. So we given the direction clockwise. Okay, now as a step 6, what we need to set up as that in each loop the summation p is 0. The summation p is this, delta p equals to 0. But this is across the loop. So we can write this for loop number 1 and we can write it for loop number 2. So this is summation, but remember that when it is direction of the loop, then we will consider it as positive, and when it is opposite to the loop direction, then we consider it as negative. And the same is applied for loop 2 also. So as you go back here and see that the flow rate in line number 1 is in the direction of loop, and in the 2 it is opposite, and in the 3 it is opposite, and in the 4 it is opposite. So the 1 and 2 are along the direction of the flow, 3 and 4 are opposite. So this way that means that the delta P from A to B plus delta P from B to C, and then minus delta P from D to E, and minus delta P from A to D, and equals to 0. So this equation we need to set up. So this equation we need to set up like this. So same equation we can set up for loop 2. So these are the two equations that we got for loop 1 and for loop 2. Now the delta P expression, so delta P means the pressure drop, which can be represented in this form that we have seen before, and we can represent this like this. This term is FQ1 square and the other terms are indicating in the C1 because we are doing it for line element 1. So we can write this form of equation. We can write this form of equation for all the lines, and which is then it looks like this form. So this is for loop 1 and then this is for loop 2. So now we have these two equations and the value of C is given here. So the values are taken positive if the flow direction is in the direction of the loop and vice versa. The above linear equations must be solved simultaneously with continuity equations at each junction. The minor losses can be taken into account, but here it has been ignored. So the minor losses can be taken into account by including the terms of discharge rather than the terms of velocity. So again, the minor losses should be taken in terms of flow rate, like the friction losses we have taken here. Okay, so this was step 6. Now moving to the step 7, set up a solution table to summarize the calculations. So now we set up a table that these are our all pipe numbers, pipe number 1, 2, 3, 4, 5, 6, 7, and we know the flow rate in each of the line. So this is for Q1, Q2, 3, 4, 5, 6, and Q7. We know the diameter of each element and we know the length of each element. So this factor we can find because the delta P, when we calculate later, then we can use directly this factor, which is C multiplied by F multiplied by Q square. So that can be written for any line element. So this is our D and L values, and these are our C values, and this is epsilon over D values. So we can prepare this table. After preparing this table, we have to identify the loop which we have already identified, that this is one loop 1 and this is loop 2. So you have to make two tables, one for loop 1 and one for loop 2. So this is here we are making that this is for loop 1, and then here we are making that this is for loop 2. Okay, so let's talk about the loop 1. So the loop 1 consists of 4 lines, line number 1, line number 2, line number 3, line number 4. So we write the certain values in this table. So we write the value, the Q, and we can make one more column for velocity, which is not here, but we can make. So we know the flow rate in these elements, element number 1, 2, 3, and 4, and then we can calculate the velocity. The velocity equals to 4 times the q over pi d square. So the d for each element, we know it, right? So we can calculate the velocity. So flow rate and velocity, and then we can calculate the Reynolds number for each element, the rho v d over mu. And we know the epsilon over d for each element, because this is we prepared in this table, that what is the epsilon over d for each element and what is the c for each element. So we prepared already for element 1, 2, 3, 4, so we can use them directly. So we know the Reynolds number. So the Reynolds number can be calculated, rho v d over mu, and then epsilon over d shall be checked, that what was the value for line number 1 and what is the value for number 2, 3, and 4. So when we want to calculate the friction factor, so basically if I say that these values we know for these lines also, right? Similarly the velocity also we know for these elements. So when we want to find out the friction factor, then we need to know three things if the flow is turbulent: Reynolds number and epsilon over d. So we calculated the Reynolds number using this expression, and then the epsilon over d, these values, and using these values we can find that what is our friction factor. So we can find the friction factor in each line, here also, here also, here also. So this is for line number 1, 2, 3, and 4. And then we can calculate the pressure drop, because the pressure drop expression is this. So we can calculate the pressure drop here for line number 1, line number 2, line number 3, and 4. So remember here that we are giving the sign the same which we have given the sign here for Q. We are giving the sign for to P is same. This is minus sign here, right? So this thing we need to understand. So now we have this table ready for loop 1, that we got the Q, we got the RE, F, and delta P, and then we make another column which is delta P over Q. So this delta P should be divided by this Q, and this delta P should be divided by this Q. So delta P over Q, we can see that these are the values. And remember that for delta P over C, because the P is also negative, Q is also negative, so delta P is over Q. So the sign will be cancelled in this case, and this value will be, and this value will be positive, which is summation. So this is summation of delta P is this, and this is summation of delta P over Q. So once we know, so for the time being, I'm not explaining this thing because we are using the delta P, right? So this is delta H. So we are solving this problem on the base of delta H. The same problem can be solved based on delta. We are solving this problem based on delta P actually, because we are using the delta P here and delta P here, but the same problem can be solved using delta H also. So the delta H we can calculate, and this is delta P divided by rho G. Okay, now coming back to this delta P. So once you calculate the delta P for all the 4 elements in the pipe, in the loop, then you calculate the summation P, and here also you calculate the summation delta P over Q. So this is basically, we can write that this delta P, and this another term is summation delta P over rho. So we can find and fill up the values in this table. So here it is Q, RE, F, delta P, and delta P over Q. And then we can find the summation values. So this value is basically the summation P, and this value is summation P over Q. So we have two summation, like this is summation delta P, and this is summation delta P over Q here. So now we need to find delta Q. So the delta Q is, by the formula, is minus delta, it is minus summation delta P, so which we have calculated here. This is summation delta P, and divided by 2 times the summation of delta P over Q. So this is the summation of delta P over Q. And when you substitute these values in this formula, then we can find that what is our delta Q. So the delta Q is coming out to be 0.0066. So this is, we will calculate, and the one table is complete here for loop 1. Now the same table, and this is the thing that before we go to the loop 2, that when you are making the program, so looking the value of f in the chart again and again is not possible. So what we do, we use the equations when we make program. So this is the equation for friction factor. So when you know the value of epsilon over d and you know the value of Re, then you can calculate what is the friction factor, and this is Chen method. So we can find the friction factor for table 1, and then we prepare the table 2, which is for loop 2. So the elements are 5, 6, 7 and 2, and remember here that the direction of the 2 is opposite to the counter to the direction in the pipeline 2. So for the 2 it is taken here negative, but the value is common for both loops. But for loop 1 it was positive because it is in the direction of loop, but here it is opposite to the direction of the loop. So here this will be taken as negative for loop 2. So that is why this is taken as negative 0.02. But in the previous table, if you see that the value is same, only the sign is different. Now in this table also, you need to calculate the Re and need to calculate the F, and then need to calculate the summation delta P, and then summation of delta P over Q. So as we can see here that, so we are able to find these values here, and we can find the summation values. This is for summation for delta P, this is summation delta P, and then this is summation delta P over Q. So these are the values here, and then substituting these values in the formula for delta P. So the formula for delta P is minus 2 summation delta P over Q delta Q. This is formula for delta Q, which is delta Q is equals to minus 2 times summation delta P over Q P here, and then this is summation delta P. So when you substitute there the values in the formula, and then we get that the delta Q comes out to be 0.0075. So now we have the both values, the delta Q for this loop 1, which is delta Q for loop 1, and then the delta Q for loop 2. So we need to correct the discharge in the loop now, because our summation of pressure drop is not 0. So it is very tedious like to bring the pressure drop 0, because we are solving the network. And so when we calculated the delta Q, so it is suggesting that you need to correct the discharge. So how do we correct the discharge? So when we correct it, that we need to find the new value for Q1, a new value for Q2, Q3, Q4, Q5, Q6 and Q7. So after finding the delta Q for loop 1 and delta Q for loop 2, so when we want to find out the new value, then it is, we will simply add the delta Q. So this is the Q1 that we have already, and then when we add delta Q for loop 1, then we will get the new value for loop 1 and Q1. So similarly, when we add the delta Q in 4, then we will get the new value of Q4. So remember that the correction delta Q1 is applicable on line number 1, line number 2, line number 3 and line number 4. So these 3, which is q1, and q3 and q4, these are belongs to loop 1, and the 5, 6 and 7, these are belongs to loop 2, where the q is common in both. So when we calculating for loop 1, we are adding the loop 1 delta q, and when we are calculating for loop 2, then we are adding the delta q for loop 2. But while we are calculating the q2 corrected value, then what we do, we are adding the delta q1 and we are subtracting the delta q from loop 2. So this is because here the fluid is flowing in the direction of the loop 1. So here we are adding, so here the flow is in the direction of the loop, here the flow is in the direct opposite to the loop. So this one we are subtracting and this one we are adding. So that is why when we calculate the new value q2, so here we are adding the delta q from loop 1, and this is the delta q from loop 2, which we are subtracting. So these things you need to take care when you are solving the network, that q2 is common for both. So the effect of delta q1 and delta q2 both should be taken into account, and it should be in this form. Okay, so after that we can continue, and then we can do the another iteration, because now we can put in the table the new value of q. So these are the new value of q, and then we can do the same thing, that we find the RE, find the F, and find the delta P, because the Q values are changed now. And then you find the delta P over Q, and then you find the summation for Q and summation for delta P over Q, and then find the delta Q for the next iterations, for the second iteration, and similarly the same thing you will do for this also. So after doing this, what we get the value of delta Q. So this is delta Q for loop 1, and which is 0.0018, and this is the delta Q for loop 2, which is 0.001. So now when you have a delta Q, then you have to again correct the discharge. You have to again correct the discharge for the Q1. So the Q1 equals to Q1 old plus delta Q from loop 1. So these things you have to do again and again until you stop the iteration. So you will be basically calculating this delta q1. You can call it new, and then you can call it like delta 1 q1 plus delta q from loop 1, and then q2 new, and this is q2 plus delta q1 minus delta q2, and then you will revise the all the discharge. So when you revise all the discharge, and then you can prepare the table for iteration 3. So this is the your corrected discharge, these are your corrected discharge. So then you prepare the table for your iteration 3, and then you again find delta q. So you have to keep doing this until your delta q is coming to be very small, and then then further corrections cannot be effective. So when the delta q is very small, so that point you can stop doing the iteration, and then you can take the solution as your final solution. So after doing the several iteration, then it come out to be that the delta q is not changing anymore, and the q values remains unaffected, remains constant, almost like very slightly changing. So those values we can consider as final values. So these are the final values of q. So here if we see a little bit about the correction discharge, so I want to explain the one step about the correction discharge. So let's see that how we are going to do that. So here what I got it, this is for loop 2, so I want to do it for loop 1 basically. Okay, this is my loop 1. So in the loop 1, my q1 is 0.006, and my delta q is 0.0066. So what will be my new q here? Q1 new equals to 0.06 and plus 0.0066. So my result is 0.066 and 6. And if I keep the accuracy up to 3 digits, so this is 0.067, rounding off the last term. This is my Q1. And similarly, we can write the Q3 new equals to Q3 plus delta Q from loop 1. So which is Q3 is minus 0.04, and then this plus 0.006. So this is like this. So we this is 6, sorry. And then when we do this, so what is our result? So what we have, like minus 0.04 and then plus 0.066. So what the result we got is 0.026. So this is going to be 0.026, and with minus sign, of course, with minus sign. No, I'm making a mistake. This is 20. So sorry, again, cancel this minus 0.04 and the plus 0.0066. This is our delta Q1. So the result is like this. So the result is not this one. So my result is minus 0.0334, and if I take the accuracy up to 3 digits, so this is minus 0.033. Okay, so similarly we can do it for Q4 also. So now our Q1 is this, delta Q1 is this value, right? So the delta Q1, and what is our delta Q2? So the delta Q1 is 0.006, and delta Q from loop 1 and from loop 2, this is, how much is that? So from loop 2 it is 0.0075. So when we do it for Q2 new, so this should be Q2 plus delta Q from loop 1 minus delta Q from loop 2. So this is going to be because the Q2, how much was Q2? When we prepare this table, the Q2 is minus 0.02. So this is going to be minus 0.02 and then plus 0.0066 and then minus 0.0075. So when we calculate this, then what is the value? So this is going to be like minus 0.02 and then plus 0.0066 and then minus 0.0075. So this comes out to be 0.0. This is going to be minus 0.020109, and for accuracy up to 3 points, this will be minus 0.021 for 3 point accurate, 3 decimal point accurate, right? So these are the values, right? So for Q1, what is our value for the Q1 is this one. For Q3, the value is this one. For Q2, the value is this one. Similarly, we can calculate Q4 also. So when we preparing the new table for second iteration, so then we have to substitute the values, the corrected values, right? So what is our corrected values? So this is the value for our Q1, which we are substituting here, right? And this is the value for our Q3, which we are substituting in the Q3, and then finally we calculate for Q2. So the Q2 is 0.21. What is the mistake we made in Q2? Is there a mistake we made in Q2? Let me check it. Oh yes, the mistake we have taken that while we substituting in this, we have taken this value from the loop 2, right? We have to take it from loop 1 actually. So because in the loop 1, this value is positive here, and in the loop 2, this value is negative here. The reason is that for the loop 1, it is in the direction of the loop, and for loop 2, it is opposite to the direction of the loop. So we should take it for loop 1 while we are doing this. So what is the correct value? This is the correct value, is the same value. The only thing is that we need to take it positive. So when we take it positive and then calculate again using the okay, so this is 0.02 and then plus 0.0066 and then minus 0.0075. So the result is basically so the result is 0.0191, and up to 3 decimal point accurate, this is 0.019. This is the value for Q2 new. So when we prepare the table for iteration 2, so this is the table for iteration 2, so here we are substituting this value, so which is 0.019, right? And when we calculate the new values for Q5, Q6, Q7, then we don't need to calculate the value for Q2 again. We will substitute the same value as here. We'll substitute the same value as here, but with negative sign, because in this loop it was opposite to the flow was opposite to the loop direction. So in this it is negative. For loop 2 it is negative. So we can calculate the Q5, Q6 and Q7 based on the delta Q2 only. Like the Q5 new is equals to Q5 plus delta Q from loop 2. And similarly the Q7 new is equals to Q7 plus delta Q from loop 2 only. And we can calculate for 6 also. So this way we can calculate these values. So this is the Q values that I wanted to explain to you. So now after the final iteration, when we got the value of Q, so these are our final solution for this problem. Now we know the Q in each of this, then it is easy for us to calculate many things. Like when we start the problem, we started the problem from here. So when we know this Q1, Q5, the Q6, and the Q4, and the Q2, Q3, and the Q7, and you know the direction of the flow, then you can easily calculate that what is your basically, so this is going to be in the opposite direction. So what is your pressure drop in each line? Here this is this direction, and here it is in the direction of the loop here, and then it is here, and then so If you want to calculate the pressure drop, then we can go along the flow path, like from here to here. We can go here to here. So this pressure and this pressure you can add to find the pressure drop from point A to C. And when you want to calculate from A to F, then you can go following this path and you can add these three elements to find the pressure drop from A to F. So basically you can find the pressure drop from any point to any point. So here we end this tutorial and about the network, and I hope you understand everything. Okay, thank you very much.